Okay, in this topic we will be exploring the difference between when we use the Vertex formula versus when we solve a quadratic equation. My name is Kurt Overhiser and I'll be your host as we look at a couple of examples of how to make this distinction. This is a college algebra topic, MAC 1105. So I've written down a word problem that we're going to look at, and it says that Bob wants to fence in a rectangular shaped vegetable garden by his house. The house will serve as one side of the garden, and Bob has 320 feet of fencing in which to build the remaining three sides. Now, due to limited space, the area of the garden must be 12,000 square feet. And we're supposed to find the dimensions of the house with the least amount of house frontage. So, as in a lot of cases, when we solve word problems, we are going to draw a picture. So, right here, this line that I'm drawing is the house frontage. That's where the house is. Since the house serves as one side of the house, we don't have to put any fencing there. But we will have to fence in the remaining sides. So we'll put it's going to be rectangular. So it looks something like that. So that rectangle represents our garden. And I'm going to label these. We don't know what the dimensions are. So that's where the algebra comes into play, and we start labeling things X, the vertical pieces, and the horizontal piece is Y. And it says that the 320 feet of fencing is going to be used for the two X's and the Y. So if I add, the first equation that I can create is I'll take the 2x's plus the 1y and set it equal to 320. That's the very first equation. And the second equation is going to be an area equation. We're going to set area, capital A for area, is going to be, we know that the area for a rectangle is length times width, or x times y. And then we're going to substitute this is the first equation, and we're going to substitute it into the second equation. So the way we're going to make the substitution is we're first going to solve the equation for y by subtracting negative 2x from both sides. And then we're going to substitute it in for y over back in equation number 2. So I put x, put parentheses, and what goes in the parentheses is what y should be equal to by a substitution from what we solved for from y in number 1, which is negative 2x plus 320. And then we're going to distribute the x. Get negative 2x squared plus 320x. Okay, now there's one number that we haven't used in the word problem yet, and that's that because of the limited space, the area of the garden must be 12,000 square feet. So in place of capital A, we're going to put that number that A represents as 12,000 square feet. Since area is measured in square units, in this case square feet, we're going to plug in for A 12,000. And then what we're going to do is we're going to get it into standard form, and I'll add 2x squared to both sides, and I'll subtract 320x from both sides. And in doing that, I get this equation. And then I can divide both sides by 2. And then when I do, I get x squared minus half of 320 is 160. Half of 12,000 is 6,000. And then 0 divided by 2 is still 0. Next, we're going to factor this. Put x here. Now, the way the signs go, they both have to be negative, because the middle sign is negative and the constant sign is positive. Two negatives multiplied together give you the positive. And then we're looking for factors of 6,000 add up to 160. And that's pretty easy. It's going to be 160. Then we use the zero product property and set each factor equal to 0. So you get x equals 100 or x equals to 60. And then what we're going to do, we'll call this x1 and x2. And then we're going to take both of these and we're going to plug them into this equation up here. And if I plug x1 equal to 100 into that equation, I'll get a corresponding y1. And when I plug that in, I get y1 equals 120. And then for y2, when I plug 60 in for x into the equation that I have the arrow pointing to, I get 200. So what this means is we have actually two configurations of the house that we're dealing with. So the first configuration, I'll draw it right here. We can put 100, 100, and then 120. And then this is Roman numeral 1, Roman numeral 2. The other configuration is going to look like this. $60 and 60, and then 200. So we got two choices. If you notice, 100 times 120 multiplies to 12,000, and also 60 times 200 multiplies to 12,000. So since we got two different configurations of the garden, we got to figure out which configuration we want. And it says, part A, find the dimensions of the house with the least amount of house frontage. Well, in Roman numeral 1, the house frontage is 120 feet. And in Roman numeral 2, the house frontage is 200 feet. The house frontage being the length or the longest side of the rectangle. So of those two, the one that's smaller is the 120 feet. So the final answer is going to be Roman numeral 1. Okay, so the dimensions of the dimensions of the garden with the least amount of house frontage is going to be 100 by 120 feet. Okay, so on to part B. With part B, we're going to use the same word problem with, I think his name was Bob, who wants to fence in a rectangular shaped vegetable garden by his house. You can see the picture right here, and here's where my house is, right here. And it's the same picture as before. The vertical fencing we'll call X, and the horizontal fencing we'll call Y. And the area is going to be X times Y. And we only have 320 feet of fencing material with which to work. So 2x plus y equals 320. You solve for y by bringing the negative 2, by subtracting 2x from both sides. You get y equals negative 2x plus 320. And we take that and substitute it in for y into the area equation. And you get area equals x times negative 2x plus 320, close parentheses. You can distribute the x and you get negative 2x squared plus 320x. Notice this is the same amount of, it's the same work at the beginning stages of part A. Where we veered off was in part A, we had to use the, because of the limited space, we had to use the area of the garden to be 12,000 square feet. And so we plugged in 12,000 in for capital A. But here in part B, we're going to take away that assumption. We're going to suppose that there are no space limitations. And we're supposed to find the maximum possible area for the garden. And some of you might think, well, if there are no space limitations, that means you can make the garden as big as you want. It could be infinitely big. But that's not true, because we still only have 320 feet of fencing with which to work. So you can't make it infinitely big, because you're going to run out of fencing eventually. But you can see what the subject to the constraint of 320 feet of fencing, you can figure out what's the most possible area that you can get for the garden. And if you look at the instructions here in letter B, I've underlined the word maximum. And underlining that word is important because that gives you a clue that you're going to be maybe using the Vertex formula. We don't have anything to plug in for A at this time because we don't have an area with which to work like we did in part A. So since we're trying to find the maximum possible area for the garden, you'll notice that the area equation is quadratic, and so it's the leading coefficient is negative 2, and that negative 2 tells you that you have a parabola that's upside down. And the negative leading coefficient tells you that the parabola is upside down, and then at the very top, or at the vertex here, you have your maximum. So we use the vertex formula in order to find the maximum point, the highest point of the parabola, since it opens downward. So we come down here, we say x is equal to the negative b divided by 2a. And of course, little a being the coefficient is negative 2. B is the middle coefficient, 320, and then C, our constant term, we don't have one, so it's 0. So taking those and plugging them in back into our vertex formula, we get negative 320 divided by 2 times a negative 2. And when you do that calculation, you get 80. So the maximum amount of area happens when x is 80 feet. So we can figure out what the y is by I'm going and we're going to use, I'm drawing a star right here. This star is what we're going to be using to plug in for y, and the star down here as well. So I'll plug in my 80 feet, so I get -2 times 80 plus 320. And I get 160 feet. So these are the dimensions of the garden. So we get 80 here, 80 here, 160 feet there. And if you find the area of this garden right here, the area would be equal to x times y, which is 80 times 160, and that's equal to 12,800 square feet. And that is the maximum area. So that is our answer right there. So notice that in part A, we were able to find the dimensions of the garden that gave us 12,000 square feet, and there were two such configurations. But it turned out that if we were a little bit more careful with the way we used our fencing, we could have squeezed out 800 square feet more space in which to work. And notice when you add up the sides, 80 plus 160 plus 80 does indeed give you 320. So hopefully when you compare parts A and B, you'll see how when it's appropriate to use the Vertex formula, -b over 2a, and when do you just solve the quadratic equation either by factoring or the quadratic formula. So anyways, I hope this helps, and good luck with your studies. See you in class.